You are listening to Scaling Node.js, a practical guide for backend development. Like and subscribe to keep up to date on our latest audiobooks. Scaling Node.js, a practical guide for backend development. 1. The quest for scale, understanding backend scalability. In the dynamic world of digital services, growth is often the ultimate aspiration. A new app takes off, a website goes viral, or a niche service finds its mainstream audience. This success, while celebrated, often brings with it an invisible, yet formidable challenge: scalability. Will your backend infrastructure groan under the weight of thousands, or even millions, of concurrent users? Or will it gracefully expand to meet the burgeoning demand? Consider the story of FlowState, an innovative meditation app launched by a small, passionate team. Their initial beta, released to a few hundred users, performed flawlessly. The app was responsive, the guided meditations streamed without a hitch, and user profiles updated instantly. Encouraged, they poured resources into marketing for a wider launch. On release day, with a surge of PR and enthusiastic social media mentions, tens of thousands of new users flocked to FlowState. Within minutes, the carefully crafted app began to unravel. Meditation sessions buffered indefinitely, profile updates failed, and eventually, the entire system ground to a halt. Users, frustrated and unable to access their calming content, deleted the app almost as quickly as they downloaded it. The FlowState team, despite having a fantastic product idea, learned a brutal lesson. A system that cannot scale with demand is a system destined to fail, regardless of its initial brilliance. They had built a beautiful car, but on a road that instantly vanished under the weight of traffic. The story of FlowState isn't unique. It's a common narrative for countless startups and even established companies experiencing unexpected success. Building a backend that works is one thing. Building one that scales is an entirely different discipline. This book is your guide to mastering that discipline within the Node.js ecosystem. What does scalable really mean? The term scalable is often thrown around loosely, frequently equated with simply being fast. While speed is undoubtedly a component, scalability is a far broader concept, encompassing several critical attributes. Performance. This is the most obvious. A scalable system performs well under increasing load. This means low latency, quick response times, and high throughput, the ability to handle many requests per second. It's about maintaining consistent speed as usage grows. Reliability. A scalable system must be dependable. It should continue to function correctly even when components fail or unexpected events occur. It's about minimizing downtime and ensuring data integrity. Availability. This refers to the percentage of time a system is operational and accessible to users. A highly available system minimizes service interruptions, ensuring users can access what they need when they need it. Think of it as the system always being on. Maintainability. As a system grows and scales, its complexity inevitably increases. A truly scalable system is also one that remains manageable, understandable, and easy to modify, debug, and update over time. This includes ease of deploying new features without disrupting existing services. At its core, scalability is the ability of a system to handle a growing amount of work by adding resources to it, without a significant drop in performance or user experience. Vertical versus horizontal scaling, two paths to growth. When we talk about adding resources, there are two fundamental approaches. Vertical scaling, scaling up. Imagine you have a single, powerful server running your application. Vertical scaling means making that one server even more powerful. You add more RAM, faster CPUs, or more storage to the existing machine. It's like upgrading from a small car to a larger, more powerful one. Pros. Simpler to manage in the short term, often doesn't require architectural changes. Cons. There's a physical limit to how large a single machine can get. You're dependent on a single point of failure. It can become very expensive for marginal gains. This was FlowState's initial approach to their backend, leading to the dead end they encountered. Horizontal scaling, scaling out. Instead of making one server bigger, horizontal scaling means adding more servers to distribute the workload. You run multiple instances of your application simultaneously, and a load balancer directs traffic to them. It's like adding more lanes to a highway or adding more identical cars to your fleet. Pros: virtually limitless potential for growth, no single point of failure, if designed well, often more cost-effective as you can use commodity hardware. Cons: introduces complexity. You need to manage multiple instances, ensure shared state is handled correctly, and design for distributed communication. This is where the bulk of scalable backend architecture lies. For modern web applications experiencing rapid growth, horizontal scaling is almost always the answer, especially when dealing with the distributed nature of the internet and global user bases. The unique challenges of backend development. Building robust backends involves navigating a landscape filled with intricate challenges. State management. In a distributed system, how do you handle user sessions or application data that needs to be consistent across multiple servers? Data consistency. Ensuring that all parts of your system see the same, accurate data, especially across multiple databases or replicated instances. Concurrency. Managing a multitude of simultaneous requests, ensuring they don't interfere with each other and are processed efficiently. Network latency. The inherent delay in communication between different servers, regions, or microservices. Security. Protecting sensitive data and access points in a complex, exposed environment. Fault tolerance. Designing systems that can withstand the failure of individual components without collapsing entirely. Observability. Knowing what's happening within your complex system. Collecting logs, metrics, and traces to understand performance and debug issues. These challenges are universal to backend development, regardless of the technology stack. However, the choices we make in our tools and architectural patterns profoundly impact how gracefully we can overcome them. Node.js, a powerful ally in the quest for scale. This is where Node.js enters the picture. Its unique architecture, built around a single-threaded event loop and non-blocking I/O, makes it exceptionally well-suited for building highly concurrent and scalable network applications. Unlike traditional multi-threaded servers that block when waiting for I/O operations, like database queries or file system access, Node.js can initiate thousands of such operations simultaneously without waiting for any single one to complete. It leverages an event-driven, asynchronous paradigm that ensures maximum utilization of server resources. Think of it this way. A traditional server is like a chef who cooks one dish at a time, waiting for each ingredient to finish cooking before moving to the next. A Node.js server, on the other hand, is like a highly efficient chef who puts multiple dishes on the stove, preps other ingredients while those dishes cook, and responds to multiple orders instantly, attending to each dish only when it's ready. This characteristic makes Node.js an excellent choice for I/O-bound applications, those that spend most of their time waiting for data to come from external sources, databases, APIs, user input, which describes the vast majority of modern backends. However, Node.js's strengths also come with considerations. Its single-threaded nature, for instance, means it's not ideal for CPU-bound tasks, heavy computations that tie up the main thread. Understanding these nuances and learning how to leverage Node.js's advantages while mitigating its potential weaknesses is key to building truly scalable systems. Your journey begins here. Over the course of this book, we will embark on a comprehensive journey. We'll start by delving deeper into Node.js's architectural foundations, unraveling how its core design principles pave the way for concurrency. From there, we'll explore various architectural patterns, from the simplicity of monoliths to the distributed nature of microservices. We'll then dive into practical techniques for horizontal scaling, master asynchronous communication patterns like message queues, and tackle the critical challenge of scaling your data layer. We'll also cover essential aspects like caching, security, API design, deployment strategies, and the vital components of monitoring and logging. By the end, you will not only understand the principles of building scalable backends with Node.js, but also possess the practical knowledge and actionable strategies to implement them, ensuring your own digital ventures gracefully grow with their success, rather than crumbling under its weight. Let's begin. 2. Node.js Unpacked: How its architecture supports concurrency. In the previous chapter, we established that scalability isn't just about speed. It's about handling growing workloads efficiently, reliably, and consistently. We also briefly touched upon Node.js's unique suitability for network applications due to its non-blocking I/O now. Let's peel back the layers and truly understand the architectural underpinnings that make Node.js a powerful platform for scalable backends. At the heart of Node.js lies a concept that often puzzles newcomers. It's single-threaded, yet renowned for high concurrency. How can a single thread manage thousands of simultaneous operations? The answer lies in its event-driven, non-blocking I/O model, powered by the V8 JavaScript engine and the libov library. The restaurant analogy, synchronous Vs, asynchronous operations. To truly grasp Node.js's secret sauce, let's use a familiar analogy, a restaurant. Scenario 1, synchronous chef blocking I/O. Imagine a small, intimate restaurant with only one chef. A customer orders a dish that requires frying. Our chef takes the customer's order, places the food in the fryer, and then stands there, waiting, watching the fryer until the food is perfectly cooked. Only after that dish is complete does he move on to the next customer's order. If the fryer takes 10 minutes, the next customer has to wait 10 minutes just to place their order. This is a blocking operation. The chef, our application's main thread, is blocked from doing anything else until the I/O frying operation finishes. This severely limits how many customers the single chef can serve concurrently. Scenario 2, asynchronous chef, non-blocking I/O. Now imagine our chef is far more efficient. He takes the first customer's order and places the food in the fryer. Crucially, he doesn't wait. He sets a timer for the frying, makes a mental note or physical reminder, and immediately turns to the next customer to take their order. While the first dish is frying, he's taking more orders, perhaps prepping vegetables for another dish, or even plating a different, already cooked meal. When the timer for the first dish goes off, a signal tells him, "Your frying is done." He then goes back, fishes out the food, and finishes that dish. This chef can handle many customers concurrently, even though he's still a single person doing all the work. This second scenario is a perfect analogy for how Node.js handles I/O operations. The chef is the single main thread of your Node.js application. The frying, which is slow and involves waiting, represents I/O operations like reading from a disk, querying a database, or making a network request. Node.js doesn't wait for these operations. Instead, it offloads them and continues processing other requests, picking up the result once the I/O operation completes. This is non-blocking I/O, the event loop, the orchestrator of asynchronicity. The mental notes and timers of our asynchronous chef are managed by something called the event loop. This is the heart of Node.js's concurrency model. The event loop is a continuous cycle that Node.js runs to process messages in a non-blocking, asynchronous manner. Here's a simplified breakdown of how it works. Call stack. When your Node.js application starts, it executes code line by line. Function calls go onto a call stack. Web APIs/Node.js APIs. When the main thread encounters an asynchronous operation, like set timeout, fsread file, or HTTP get, it doesn't execute it directly. Instead, it passes this operation to a behind-the-scenes part of Node.js, which uses libov, similar to sending it off to a worker. Callback queue task queue. Once the asynchronous operation completes, e.g., the file is read, the HTTP request returns, its associated callback function. The code that should run when the operation finishes is placed into a callback queue. The event loop. This is the core mechanism. It continuously monitors two things. Is the call stack empty? Is the main thread free? Is there anything in the callback queue? If the call stack is empty, the event loop takes the first callback from the queue and pushes it onto the call stack for execution. This cycle repeats indefinitely. This constant looping and checking ensure that the main thread is never idle when there's work to be done. It handles synchronous code, offloads asynchronous tasks, and then processes the results of those tasks once they are ready. Libov, the unsung hero. While the V8 JavaScript engine, developed by Google for Chrome, executes your JavaScript code, it's actually libov, a C++ library that provides Node.js with its powerful asynchronous I/O capabilities. libov handles the heavy lifting of interacting with the operating system's underlying subsystems for things like file system operations, reading and writing files, networking, handling HTTP requests, TCP connections, DNS resolution, looking up domain names, child processes, spawning external processes. When Node.js encounters an I/O operation, it delegates it to libov. Libov then uses its own thread pool, separate from the main JavaScript thread, to perform these potentially blocking operations efficiently in the background. Once an operation completes, libov notifies the event loop, which then schedules the corresponding callback function to be executed by the main JavaScript thread. This division of labor allows the main thread to remain non-blocked and responsive. Asynchronous programming, promises, async await. To effectively work with the non-blocking nature of Node.js, asynchronous programming patterns are essential. Historically, callbacks, function, error data were used, often leading to callback hell or deeply nested, hard-to-read code. Modern Node.js development primarily relies on promises and the async await syntax, which are built on top of promises. Promises. A promise is an object representing the eventual completion or failure of an asynchronous operation and its resulting value. Instead of passing a callback directly, an asynchronous function returns a promise. You can then attach to handle success, or catch to handle errors. Conceptual example, not actual runnable code for book. Fetch user data, user ID. Then data equals process user data. Catch error equals handle error. Async await. This syntax provides a more synchronous-looking way to write asynchronous code, making it cleaner and easier to read, especially when dealing with multiple sequential asynchronous operations. The await keyword pauses the execution of an async function until the promise it's waiting on settles, resolves, or rejects. Conceptual example. Async function get user and orders, user ID. Try const user data equals await fetch user data, user ID. Pause here until complete. Const orders equals await fetch user orders, user date ID. Pause here. Return user data, orders, catch error. Console error, failed to fetch data, error, throw error. These constructs make it much simpler to manage complex asynchronous flows, contributing directly to maintainability, one of our 4 pillars of scalability. The elephant in the room. CPU-bound tasks. While Node.js excels at I/O-bound tasks, its single-threaded nature means it struggles with CPU-bound tasks. These are operations that require significant computational power and tie up the CPU for extended periods. Examples include complex data encryption-decryption, heavy image or video processing, intensive mathematical calculations, large data compression-decompression. If the main Node.js thread is busy with a CPU-bound task, it cannot process other incoming requests or callbacks from the event loop. The entire application will become unresponsive or blocked until the CPU-intensive task finishes. For a scalable backend, this is a critical bottleneck. To mitigate this, Node.js introduced worker threads, leveraging multi-core processors. Introduced with Node.js 10.5.0 and stabilized in Node.js 12, worker threads allow you to run CPU-intensive JavaScript operations in a separate thread, isolated from the main event loop thread. This means your main application thread remains responsive, continuing to handle incoming requests and other I/O operations, while the heavy computation happens in the background. Worker threads operate similarly to web workers in browsers. They communicate with the main thread by passing messages, rather than sharing memory directly, though array buffers can be transferred. This provides a safe and efficient way to distribute CPU-bound workload across multiple CPU cores without blocking the main event loop. Conceptual worker thread usage. Main thread. Const worker equals new worker, /worker.js. Worker post message, number 40, worker on message, result equals console, log factorial. Result, worker.js. Parent port on message, number equals. Const result equals calculate factorial number. CPU intensive calculation. Parent port post message, result. This capability is crucial for Node.js backends that might encounter occasional heavy computational demands, allowing them to remain high-performant and scalable. Summary: Node.js's foundation for scaling. In essence, Node.js achieves high concurrency and efficiency in backend systems through non-blocking I/O. It doesn't wait for slow operations to complete, instead offloading them. The event loop, the intelligent orchestrator that ensures the main thread is always busy with available work. Libov, the powerful underlying C++ library handling system-level asynchronous tasks. Modern asynchronous patterns, promises, async await, making asynchronous code manageable and readable. Worker threads, a solution for offloading CPU-bound tasks to separate threads, preventing the main thread from blocking. Understanding these core architectural components is fundamental to designing and building Node.js backends that can truly scale. It empowers you to write efficient code, identify potential bottlenecks, and leverage the platform's strengths to their fullest. With this foundation, we can now explore how to structure our applications for increasing demand. 3 architectural foundations, from monoliths to microservices. Having grasped the core characteristics of Node.js that enable concurrency, we now turn our attention to the higher-level structures for building backend systems. Just as a building needs a blueprint, a software system needs an architecture, a design that dictates how its components interact. The choices you make here profoundly impact your system's scalability, maintainability, and ability to adapt to future demands. We'll explore 3 primary architectural styles common in backend development: the traditional monolith, the distributed microservices approach, and the increasingly popular serverless model. Each has its place, its benefits, and its challenges, especially concerning scalability with Node.js. The monolithic architecture. Simplicity for starters. A monolithic architecture is like a single, large, self-contained application. All functions, user authentication, product catalog, payment processing, order management, etc., are bundled together within a single codebase and deployed as a single, indivisible unit. Imagine a traditional e-commerce application. In a monolith, the code for managing user accounts, listing products, handling shopping carts, and processing payments all reside within the same Node.js application. This application connects to a single database and runs as one process, or perhaps a few identical processes if using Node.js's cluster module for basic horizontal scaling, as we discussed briefly. Pros of monolithic architecture. Simpler to develop and deploy initially. For small teams and new projects, a monolith is often the fastest way to get started. All code is in one place, reducing setup complexity. Easier debugging. When all components are in the same process, tracing execution flow and debugging issues can be straightforward. Unified testing. Testing the entire system can be simpler as you're testing one large unit. Less operational overhead initially. You only have one application to deploy, manage, and monitor. Cons of monolithic architecture, especially for scalability. Scaling challenges. This is the primary hurdle. When one part of the application experiences high load, e.g., product browsing, you have to scale the entire application, even the parts that aren't under stress, e.g., payment processing, which might have low usage. This leads to inefficient resource utilization. Tight coupling. Components are often deeply intertwined. A change in one module might unintentionally affect others, increasing complexity and risk. Technology lock-in. It's hard to introduce new technologies or switch frameworks for specific parts without rewriting the entire application. Slow development pace. Over time, as the codebase grows, it becomes harder for multiple teams to work on it concurrently without conflicts. Build times and deployment times can become excessively long. Single point of failure. If the monolithic application crashes, the entire service goes down. When to consider a monolith with Node.js. Monoliths are often a good starting point for new, small projects, where requirements are still evolving and speed to market is critical. Small teams, where the complexity of distributed systems would outweigh the benefits. Projects with clear, limited scope that are not expected to experience rapid, unpredictable growth in specific areas. A Node.js monolith would leverage Express.js or Fastify, connect to a database like PostgreSQL or MongoDB, and perhaps use the cluster module for basic multi-core utilization. It's a perfectly valid architectural pattern for many applications, especially in their early stages. However, as the story of flow state illustrated, they can quickly hit limits when unexpected success arrives. The microservices architecture, distributed for growth. Microservices architecture is a style that structures an application as a collection of loosely coupled services. Each service is independently deployable, focuses on a single business capability, and communicates with other services, typically over a network through well-defined APIs, application programming interfaces. Returning to our e-commerce example, a microservices architecture would break it down into separate, independent services: a user service, a product catalog service, a shopping cart service, an order service, and a payment service. Each service might have its own database, its own code base, and can be developed, deployed, and scaled independently. Pros of microservices architecture for scalability. Independent scalability. This is its prime advantage. If the product catalog service is overwhelmed, you can scale only that service by adding more instances, leaving other services untouched. This leads to efficient resource utilization. Technology diversity. Different services can use different programming languages, frameworks, or databases best suited for their specific task. A Node.js service for real-time order updates, a Python service for analytics, and a Java service for complex legacy integrations can coexist. Improved fault isolation. If one microservice fails, it doesn't necessarily bring down the entire application. Other services can continue to function. Faster, independent deployments. Teams can develop and deploy their services without waiting for or affecting other teams, accelerating the development cycle. Easier for large teams. Small, focused teams can own specific services, improving team autonomy and productivity. Cons of microservices architecture. Increased complexity. This is the biggest drawback. Managing many independent services, deployment, monitoring, service discovery, distributed transactions, is inherently more complex than managing a monolith. Inter-service communication overhead. Network calls between services are slower than in-process calls. Data consistency challenges. Ensuring data consistency across multiple databases owned by different services can be difficult. Distributed transactions are complex. Operational burden requires robust DevOps practices, automation, CI/CD, and advanced monitoring tools. Debugging difficulties. Tracing requests across multiple services can be challenging. Node.js in a microservices context. Node.js is an excellent fit for building microservices due to its lightweight nature. Its fast startup times and low memory footprint make it ideal for quickly spinning up and tearing down service instances. Event-driven model. Naturally aligns with message queues and event bus patterns, often used for async communication between microservices, which we'll cover in Chapter 5. JSON native. Very efficient for handling JSON data, which is the primary data interchange format for REST-TFL and GraphQL APIs between services. Key components in a microservices architecture. API gateway, a single entry point for all clients. It routes requests to the appropriate microservice, handles authentication, rate limiting, and other cross-cutting concerns. Service discovery, a mechanism for services to find and communicate with each other, e.g., Console, Eureka. Message brokers, event buses, for asynchronous communication and decoupling services, e.g., RabbitMQ, Kafka. Containerization, Docker, and orchestration, Kubernetes. Essential for deploying, managing, and scaling microservices efficiently, as discussed in Chapter 10. When to consider microservices, large, complex applications that are expected to evolve significantly over time. Large organizations, multiple teams, where independent development and deployment are crucial. High-scale applications, where different parts of the system have vastly different scaling requirements. As a strategic move, when a monolith is becoming a bottleneck and hindering growth, it's important to stress that microservices are not a silver bullet. They introduce significant complexity and operational overhead. Martin Fowler, a renowned software architect, wisely advises, don't start with microservices. Instead, you shouldn't start with a microservices architecture unless you have a system that is too complex for a monolith. This brings us to the Goldilocks principle. Find what's just right for your current needs. Serverless architecture, function as a service FaaS, event-driven simplicity. Serverless architecture takes the concept of abstracting infrastructure a step further. With FaaS, you write individual functions, typically small pieces of code that perform a single task, and deploy them to a cloud provider, like Oz Lambda, Google Cloud Functions, Azure Functions. The cloud provider then manages all the underlying infrastructure: servers, operating systems, scaling, maintenance. Your function runs only when triggered by an event, e.g., an HTTP request, a file upload, a database change, and you pay only for the compute time your function actually uses. For our e-commerce example, individual operations could become serverless functions. A process product image function that runs when a new image is uploaded, an add user newsletter function when a user signs up, or a process payment function triggered by an order event. Pros of serverless architecture for scalability. Automatic scaling. This is its biggest advantage for scalability. Cloud providers automatically scale your functions from 0 to thousands of instances based on demand. You literally don't have to think about servers. Reduced operational overhead. No servers to provision, patch, or manage. This significantly lowers DevOps efforts. Pay-per-execution cost model. You only pay when your code runs, which can be very cost-effective for intermittent workloads. High availability by default. Cloud providers build in high availability and fault tolerance. Cons of serverless architecture. Vendor lock-in. Your code and deployment pipeline become tightly coupled to a specific cloud provider's FaaS ecosystem. Cold starts. If a function hasn't been invoked recently, it might take a few seconds longer for the first request to spin up a new instance. Cold start. Statelessness. Functions are fundamentally stateless. Managing state requires external services, databases, caches, message queues. Monitoring and debugging. Distributed nature can make debugging and monitoring challenging, especially tracking execution across multiple functions. Execution limits. Functions often have memory, CPU, and execution duration limits. Node.js in a serverless context. Node.js is extremely popular for serverless functions due to fast startup times. Node.js functions generally have lower cold start times compared to some other runtimes like Java. Small footprint. Its lightweight nature translates to less memory usage and faster deployment. Native async support naturally fits the event-driven model of serverless functions. When to consider serverless, event-driven workflows, where tasks are triggered by specific events, e.g., image resizing, real-time data processing. APIs with fluctuating traffic, where automatic scaling without manual intervention is a major benefit. Backend for front-end, BFF, patterns, simple API endpoints that aggregate data. Offloading compute-intensive tasks without managing dedicated servers. The Goldilocks principle, choosing the right architecture. There's no one-size-fits-all answer to which architecture is best. The Goldilocks principle applies. You need to find the one that's just right for your current situation, considering factors like team size and skill set. Small teams might struggle with the complexity of microservices. Project stage. A brand new startup usually benefits from the speed of a monolith. Anticipated growth. If explosive growth is certain in specific areas, plan for modularity. Business domain complexity. Some domains naturally lend themselves to being broken into independent services. Often, architectural evolution is the real story. Many successful companies start with a monolith to gain traction, and as they grow and encounter specific scaling pain points, they strategically extract microservices from the monolith, typically starting with high traffic or highly complex components. This controlled decomposition allows them to leverage Node.js's strengths for specific services while slowly embracing the benefits of distributed systems. Serverless functions can then be layered on top for particular event-driven tasks. Understanding these architectural styles is the first step toward building scalable Node.js backends. In the next chapter, we will dive into the practical implementation of horizontal scaling within Node.js, showing you how to distribute your application's workload across multiple instances, regardless of whether you're working with a monolith or microservices. For horizontal scaling, harnessing Node.js clustering and load balancing. In the previous chapter, we explored the foundational architectural styles and established that for ambitious, growing applications, horizontal scaling out, is the path toward virtually unlimited capacity. Instead of making one server bigger, we add more servers. Now, let's dive into the practical mechanisms for achieving this with Node.js, focusing on both internal Node.js capabilities and external infrastructure. The problem: Node.js is single-threaded by default. As we learned in Chapter 2, a Node.js application runs as a single process, and by default, utilizes only one CPU core. Modern servers typically come with multiple CPU cores. While Node.js's event loop brilliantly handles concurrent I/O operations, it cannot inherently distribute computational load across all available cores on a multi-core machine. This means a single Node.js process cannot fully saturate a multi-core server, leaving precious CPU cycles unused. If you have an 8-core CPU and your Node.js application is running on just one core, you're only utilizing 1/8 of your server's processing power for JavaScript execution. This is a significant bottleneck for applications seeking maximum performance from their existing hardware. The solution: Node.js Cluster Module. Node.js offers a built-in solution to this problem, the cluster module. This module allows you to take full advantage of multi-core systems by easily creating worker processes that share the same server port. Here's how the cluster module works conceptually. Master process. You designate one process as the master. Its primary role is to create and manage worker processes. It doesn't typically handle requests itself. Worker processes. The master process forks, creates copies of itself, and these copies become the worker processes. Each worker process runs its own instance of your Node.js application, effectively operating as if it were an independent server. Load distribution. The master process automatically handles distributing incoming connections to the worker processes using a round-robin approach, or potentially other methods depending on the operating system and Node.js version. Conceptual example in a traditional server.js file. Conceptual example for the book. Const http equals require http, const numcpus equals require os, cpus, length, get number of CPU cores. Our simple HTTP server logic. Const server logic equals rec, raise equals, simulate some I/O or slight processing. Set timeout equals, res write head 200 content type. Text plain, resend hello from Node.js process bid \n, 10, if this is the master process. If require cluster is master. Console log, master process bid is running. Fork workers. For let I equals 0, I numcpus, I++. Require cluster, fork. Require cluster, on exit, worker code signal equals. Console log, worker.processBid died. Restarting, require cluster, fork, replace dead worker. Else, if this is a worker process, just run the server. HTTP create server logic. Listen 3000 equals. Console log, worker process bid, started on port 3000. When you run this script, the master process will start, detect your number of CPU cores, and then fork an equal number of worker processes. Each worker process will listen on the same port, e.g., 3000. Incoming requests will be distributed among these workers, allowing your Node.js application to utilize all available CPU power on that single machine. Benefits of cluster module: max CPU utilization. Effectively uses all cores on a single machine. Increased throughput, can handle more requests per second. Improved resilience, basic. If one worker crashes, others continue to serve requests, and the master can even restart the failed worker. Limitations of cluster module: single machine only, cannot scale beyond a single physical or virtual machine. State management: Workers are isolated processes and do not share memory. Any in-memory state, e.g., session data, cached items, would not be shared across workers, requiring external solutions like RIDIs for sessions. Overhead. While minimal, there's some overhead in managing multiple processes. For these reasons, the cluster module is a vital tool for vertical scaling within a single Node.js instance, but it's often complemented by, or superseded by, external load balancing for true horizontal growth. Worker threads versus child processes, and cluster. It's important to distinguish between cluster, which forks new child process instances, and worker threads introduced in Node.js 10 and 12, as discussed in Chapter 2. Child process, used by cluster, runs entirely separate Node.js instances, each with its own V8 instance, event loop, and memory space. Communication between them requires explicit IPC interprocess communication, ideal for entirely separate workloads or for distributing web requests. Worker threads runs JavaScript code in isolated threads within the same Node.js process. They share some memory resources efficiently, like array buffers, but still manage their own event loops. Ideal for offloading CPU-bound tasks to keep the main thread responsive. While cluster is about scaling requests horizontally across cores, worker threads are about scaling computation within a single Node.js instance without blocking its event loop. Both are crucial for maximizing performance from your hardware. Process managers, keeping your Node.js apps alive and healthy. For production environments, directly managing Node.js cluster logic, process restarts, and monitoring manually is impractical. This is where process managers come in. Tools like PM2, Process Manager 2, Forever, or Systemed are designed to keep your Node.js applications running continuously, restart them if they crash, and provide basic load balancing across CPU cores. PM2, a popular choice. PM2 is a production process manager for Node.js applications with a built-in load balancer. Automatic clustering. PM2 can automatically fork your application into multiple processes using the cluster module, distributing the load across CPU cores without you writing the cluster code yourself. You just tell it how many instances to run. Application monitoring provides statistics about CPU, memory, and requests per second. Log management manages application logs. Automatic restarts recovers gracefully from crashes, ensuring high availability. Hot reloads allows you to deploy new code without downtime. Conceptual PM2 usage. Start your app in cluster mode with X instances, e.g., matching CPU cores. PM2, start app.js imax. List running processes. PM2 list. Monitor processes. PM2 monit. Stop all processes. PM2 stop all. Using a process manager, like PM2, simplifies the operational management of Node.js applications on a single server, making it far more robust and able to utilize all CPU resources. External load balancing, distributing traffic across multiple machines, while cluster and process managers like PM2 scale your Node.js application across CPU cores on a single machine. True horizontal scaling happens when you distribute traffic across multiple machines, servers, virtual machines, or containers. This is the role of an external load balancer. An external load balancer sits in front of your multiple Node.js application instances, which could each be running in cluster mode or as single processes within containers. When a request comes in, the load balancer receives it first and then intelligently routes it to one of the available healthy application instances. Types of load balancers: hardware load balancers, dedicated physical devices. Expensive but high performance. Software load balancers, software running on commodity servers, more flexible and cost-effective. Examples include Nginx, HA Proxy, Envoy, or cloud provider solutions like AWS Elastic Load Balancer, ELB, Google Cloud Load Balancing, or Azure Load Balancer. DNS load balancing. Simple but less effective, as it relies on DNS resolution and doesn't consider server health. Load balancing algorithms, how they choose a server. Round robin. Routes requests sequentially to each server in the pool. E.g., request 1 to server A, request 2 to server B, request 3 to server C, request 4 to server A, etc. Least connections routes requests to the server with the fewest active connections, ensuring busy servers aren't overloaded. IP hash directs a client's request to the same server based on their IP address, useful for stateful applications. Weighted load balancing allows you to assign weights to servers, directing more traffic to more powerful or less busy servers. The challenge of shared state, session stickiness. When requests for the same user might hit different servers in a horizontally scaled environment, managing session data becomes a critical challenge. If a user logs in and their session information is stored in server A's memory, and their next request is routed to server B won't know they're logged in. Solutions to this include session stickiness, sticky sessions. The load balancer is configured to direct all requests from a particular user, e.g., based on their IP address or a cookie, to the same backend server. Pros: simplest to implement, as it requires no changes to your application. Cons: reduces true load balancing effectiveness. Some servers might get disproportionately more traffic. Makes server maintenance harder. Can't just take a server down without disrupting active sessions. Creates a single point of failure within the distributed system. If the sticky server dies, the session is lost. Generally discouraged for high scalability needs. External session store, the preferred and more robust solution. Instead of storing session data in the application's memory, you store it in an external, highly available, and scalable data store, accessible by all your Node.js instances. Common choices for this include Redis or Memcached, which we will cover in more detail in Chapter 7 about caching. By externalizing sessions, each Node.js instance becomes fundamentally stateless with respect to user sessions. Any request can be served by any instance, allowing for seamless horizontal scaling and easy server replacement or removal. Putting it all together, a scalable setup. A typical scalable Node.js backend setup often combines these elements: multi-machine deployment, multiple virtual machines or containers running your Node.js application. Process manager, e.g., PM2. Each machine running Node.js can use PM2 to manage its local Node.js processes, leverage cluster for multi-core utilization, and maintain high availability on that specific machine. External load balancer sits in front of all your machine's containers, distributing incoming web traffic across them. External shared state, e.g., Redis, handles sessions, cache data, or other shared information that needs to be accessible by all application instances. This layered approach allows your Node.js application to handle a massive number of concurrent requests, gracefully scaling from a single server to a globally distributed system. In the next chapter, we'll delve into refining this by exploring how to handle asynchronous tasks and background processes, further enhancing your backend's responsiveness and overall scalability. 5. Asynchronous mastery. Message queues, event streams, and background tasks. In our journey toward building scalable Node.js backends, we've learned how Node.js excels at non-blocking I/O and how to horizontally scale our application processes to handle more concurrent requests. However, what happens when a user's request triggers an operation that's inherently slow or resource-intensive, like sending a welcome email, processing an image upload, or generating a complex report? If these tasks are performed directly within the HTTP request-response cycle, they can significantly degrade user experience, leading to slow response times, timeouts, and ultimately, frustrated users. This is where asynchronous processing comes into its own. By decoupling long-running or non-essential tasks from the immediate user interaction, we can improve responsiveness, enhance fault tolerance, and achieve greater throughput. The key tools for this mastery are message queues and event streams, often used for managing background tasks. The problem: long-running operations in the request cycle. Imagine a social media platform built with Node.js. When a user uploads a new profile picture, several things might need to happen. Save the original image to cloud storage. Resize the image to multiple dimensions: thumbnail, medium, large. Apply watermarks or filters. Update the user's profile in the database. Notify close friends about the new picture. If your Node.js application attempts to do all of this synchronously within the HTTP request handling function, the user will experience a significant delay. If the operations take too long, e.g., 5 to 10 seconds, the request might even time out, leading to a failed upload despite everything eventually working in the background. This creates a poor user experience and ties up your application's valuable processes during the wait, reducing its capacity to serve other users. The solution: decoupling with message queues. The elegant solution is to decouple these long-running tasks. Instead of performing them immediately, the Node.js application simply logs a to-do item for another process to handle. This to-do list is precisely what a message queue provides. A message queue is a form of asynchronous service-to-service communication used in serverless and microservices architectures. Messages are stored in a queue until they are processed and deleted. Each message is processed only once by a single consumer. Key components of a message queue system: producer, publisher, the component that creates and sends messages to the queue. In our example, this would be your Node.js API server handling the image upload request. Queue, a durable buffer where messages are stored temporarily. It acts as an intermediary, ensuring messages aren't lost if consumers are busy or unavailable. Consumer worker, the component that retrieves messages from the queue and processes them. This would be a separate Node.js worker process specifically designed to handle image processing. Conceptual flow with a message queue. User uploads image to Node.js API. Node.js API receives image, saves original to storage. Node.js API creates a message, e.g., type, process image, userid, size, image URL, s3//bucket/original.jpg. Node.js API sends this message to a message queue and immediately returns a 202 accepted response to the user, indicating that the upload was received and is being processed. A separate Node.js worker process, the consumer, constantly listening to the message queue, picks up the process image message. The worker process performs all the time-consuming tasks: resizing, watermarking, notifying friends, updating the database. Benefits of message queues for scalability: improved responsiveness. The user gets an immediate response, enhancing their experience. Increased throughput. The main API server is quickly freed up to handle more incoming requests. Decoupling. Producer and consumer are independent. They don't need to know about each other's availability or implementation details. This makes your system more modular and easier to maintain. Buffering and resilience. If a worker process goes down, messages remain in the queue until another worker becomes available. This prevents data loss and makes your system more fault-tolerant. Load leveling handles bursts of traffic by queuing requests during peak load and processing them when capacity frees up. Independent scaling. You can scale the number of API servers, producers, and image processing workers, consumers, independently, based on their respective loads. Popular message queue technologies suitable for Node.js. RabbitMQ, a general-purpose message broker implementing the Advanced Message Queuing Protocol, AMQP. Very robust, feature-rich, and widely used. Redis as a message broker. While primarily a caching tool, Redis's list data structure and pub/sub capabilities can be used for simple message queuing, especially for background jobs. Kafka, a distributed streaming platform, excellent for high-throughput, high-volume data streams. More on this with event streams. Amazon SQS SNS, Google Cloud PubSub, Azure Service Bus. Managed message queuing services offered by cloud providers, reducing operational overhead. Event streams. Beyond simple queues. While message queues are excellent for individual, discrete tasks, event streams, often powered by technologies like Apache Kafka or similar cloud services, are designed for a continuous flow of data or events. Each event represents something that happened in the system, e.g., user signed up, order placed, product viewed. Instead of messages being consumed and deleted, events are typically durable and can be read by multiple consumers, potentially at different times. Key differences between message queues and event streams. Consumption. Queue messages are typically consumed by one consumer and then removed. Events in a stream are persistent and can be consumed by multiple, independent consumers. Ordering. Queues generally guarantee message order, FIFO. Event streams guarantee order within a partition, but not necessarily globally across all partitions. Use case. Queues are for decoupling tasks. Streams are for enabling real-time data processing, auditing, and building reactive microservices. Example use cases for event streams. Real-time analytics. Track user behavior in real time by processing product-viewed events. Data replication. Replicate database changes across multiple systems. Complex event processing. Trigger multiple side effects from a single event, e.g. order-placed event triggers inventory update, payment processing, notification to shipping, and analytics logging. Node.js is well-suited for both producing and consuming events from streams due to its non-blocking I/O, allowing it to efficiently handle high volumes of incoming event data or rapidly publish events. Implementing background job processing in Node.js. Once you've chosen a message queue or streaming technology, you'll need a way for your Node.js applications to interact with it and define the background tasks. Common patterns. Dedicated worker processes. As mentioned earlier, run separate Node.js applications specifically designed to be consumers of your message queue. These worker processes continuously poll the queue or listen for incoming messages and execute the associated task logic. Libraries. Libraries like Bulk, built on Redis or QOlder, also Redis-based for Node.js, provide excellent abstractions for managing jobs, retries, concurrency, and progress tracking with Redis as the backend. Conceptual BullMQ producer within your main API server. Const queue equals require Bulk. Const image processing queue equals new queue image processor. App post/upload async rec raise equals save image await image processing queue add process image URL add job to queue res status 202 send image upload received processing in background a conceptual BullMQ worker in a separate Node.js process. Const worker equals require Bulk. Const worker equals new worker image processor async job equals console log processing image job date image URL perform CPU I/O intensive image processing here. Await simulate image processing 5000 simulate 5-second task. Console log image job date image URL processed. Serverless functions. For certain types of background tasks, serverless functions like Oz Lambda Google Cloud Functions with event triggers are an ideal solution. For example, a Lambda function can be triggered directly by a new file upload to S3, cloud storage, or by a message being published to a cloud message queue. This completely removes the need to manage worker servers. Choosing a strategy. Simple background tasks, e.g., sending emails. A simple Redis-backed job queue library like Bulk with a dedicated Node.js worker can be sufficient. High-volume, real-time data processing. Apache Kafka or cloud-managed streaming services are typically recommended for their throughput and durability characteristics. Event-driven microservices. Kafka or cloud-managed event buses facilitate communication between loosely coupled services. Sporadic, event-triggered tasks. Serverless functions are excellent for their cost-effectiveness and automatic scaling. The power of decoupling. By mastering asynchronous processing using message queues and event streams, you gain immense power to design highly scalable, resilient, and performant Node.js backends. You transform bottleneck operations into background jobs, freeing up your main application processes and ensuring a smooth, responsive experience for your users. This decoupling is a cornerstone of robust distributed systems and plays a crucial role as your application grows and evolves. In the next chapter, we will shift our focus to perhaps the most common bottleneck in any scalable application, the data layer. 6. Data layer scalability, choosing and taming your databases. We've covered how to scale your Node.js application logic, whether across CPU cores or multiple machines, and how to offload background tasks to improve responsiveness. However, a highly scalable application tier is often only as good as its data layer. The database, where your application's critical information resides, is frequently the primary bottleneck in a growing system. This chapter will delve into strategies for scaling your data layer, covering database choices, architectural patterns, and practical considerations for Node.js backends. The problem: your database is often the bottleneck. As your application attracts more users and processes more data, your database faces increasing pressure. Read load: every user visiting a page, searching for a product, or viewing their profile generates read queries. Write load: every new user signup, order placement, or content upload generates write, insert, update, delete queries. Data volume: simply the sheer amount of data stored can impact query performance and storage costs. Concurrency: handling hundreds or thousands of simultaneous reads and writes requires robust database management. If your database can't keep up, your entire application grinds to a halt, regardless of how many Node.js instances you're running. SQL versus NoSQL: choosing the right tool for the job. The first critical decision in designing a scalable data layer is often the choice between a relational database, SQL, and a non-relational database, NoSQL. Neither is inherently better for scalability. They offer different strengths. Relational databases, SQL. Examples: PostgreSQL, MySQL, SQL Server, Oracle. Characteristics: organize data into highly structured tables with predefined schemas. Data is related using foreign keys. Emphasize ACID properties: atomicity, consistency, isolation, durability, which are crucial for transactional integrity, e.g., financial transactions. Strengths for scalability: data integrity. Strong consistency guarantees ensure data is always accurate and reliable. Complex queries: SQL, structured query language, is powerful for complex joins across multiple tables and aggregations. Mature ecosystem: robust tooling, widely understood extensive community support. Challenges for scalability: vertical scaling bias, traditionally scale up more powerful servers. Scaling horizontally often requires more complex setups, sharding, replication. Schema rigidity: changing schemas can be difficult and disruptive, especially with massive datasets. Joins performance: complex joins can become slow with large tables. Non-relational databases, NoSQL. Examples: MongoDB document, Cassandra column family, Redis key value, Neo4j graph. Characteristics: offer more flexible schemas or no schema at all. Data is stored in formats other than traditional tables, designed specifically for scalability and high performance across distributed systems. They often prioritize base properties, basically available, soft state, eventual consistency, over strict ACID properties. Strengths for scalability: horizontal scalability, often designed to scale out easily by distributing data across many servers, sharding partitioning built in. Flexible schemas adapt quickly to changing data requirements without complex migrations. High write performance can handle massive write loads. Optimized for specific workloads. Different NoSQL types are optimized for different access patterns, e.g., document databases for JSON, key value stores for caching. Challenges for scalability: consistency trade-offs may offer eventual consistency, which means data updates might take time to propagate across all nodes. Less mature ecosystem: compared to SQL databases, some NoSQL options have less mature tooling or smaller communities. Complex queries often lack a standardized query language like SQL. Complex relationships or ad hoc queries can be difficult or require application-level handling. Denormalization management: while flexible, managing denormalized data requires careful application design to ensure consistency. Node.js and database choice. Node.js, being JavaScript native and JSON-friendly, integrates very naturally with document databases like MongoDB. MongoDB stores data as JSON-like documents, which aligns perfectly with JavaScript objects. This often reduces the impedance mismatch between your application code and the database, speeding development. However, Node.js also has excellent drivers for relational databases like PostgreSQL, e.g., PG, or SQLize. The best choice depends entirely on your data's structure, consistency requirements, query patterns, and anticipated scaling needs. Many large-scale applications use a polyglot persistence approach, using different database types for different microservices or data types, leveraging the strengths of each. Scaling strategies for your database. Once you've chosen a database type, you need strategies to cope with increasing load and data volume. 1. Vertical scaling, scaling up. Method: upgrade your existing database server with more powerful hardware, more RAM, faster CPUs, SSDs. Pros: simplest to implement, no application changes needed. Cons: hardware limits exist, eventually hitting a ceiling. Can be very expensive for maximum tier machines. Single point of failure. 2. Replication. Method: create multiple copies, replicas of your database. You typically have one primary, master database that handles all writes and several secondary, read replicas that handle read queries. Data is asynchronously replicated from the primary to the secondaries. Pros: read scaling. Dramatically increases read throughput. Your Node.js application can direct read queries to any of the replicas and write queries only to the primary. This is particularly effective for read-heavy applications, which most web applications are. High availability. If the primary fails, one of the secondaries can be promoted to become the new primary, minimizing downtime. Cons: write bottleneck. Writes still funnel through a single primary, so this doesn't help write scaling directly. Eventual consistency. Replicas might be slightly behind the primary, leading to temporary inconsistencies, read after write consistency issues. Your application needs to be aware of this. 3. Sharding, partitioning. Method: divide your data into smaller, independent chunks called shards or partitions, and distribute these shards across multiple database servers. Each shard contains a subset of the total data and is completely independent. Pros: write scaling. Spreads write load across multiple servers, as different pieces of data are written to different shards. Massive scalability. Can scale to extremely large datasets and high query loads that a single database instance could never handle. Improved performance. Queries only need to hit the relevant shard, reducing the amount of data scanned. Cons: complexity. Most complex scaling strategy. Requires careful planning of the sharding key, the column used to determine which shard data belongs to. Application changes. Your Node.js application needs to be aware of the sharding logic to direct queries to the correct shard. Data rebalancing. Adding new shards or rebalancing existing data is very challenging. Distributed transactions. Transactions across multiple shards are exceptionally difficult to maintain ACID properties. Choosing a sharding strategy, range-based sharding. Data is split based on a range of the sharding key, e.g., userid 1 to 1000 on shard 1, 1001 to 2000 on shard 2. Can lead to hot spots if certain ranges are more active. Hash-based sharding. Data is distributed randomly using a hash of the sharding key. Provides more even load distribution, but makes range queries harder. NoSQL databases like MongoDB and Cassandra have sharding built in, making it significantly easier to implement compared to SQL databases, where it often requires external tools or careful manual management, e.g., with PostgreSQL's table partitioning or specific sharding proxies. 4. Connection pooling. Regardless of your chosen database or scaling strategy, connection pooling is critical for any Node.js application interacting with a database. Creating a new database connection for every request is expensive and slow. A connection pool maintains a set of open, reusable connections to the database. How it works. When your Node.js application needs to query the database, it obtains a connection from the pool. Once the query is done, the connection is returned to the pool for reuse. Benefits: reduced overhead. Avoids the costly process of establishing new connections for every request. Improved performance, faster query execution. Controlled concurrency. Prevents the database from being overwhelmed by too many simultaneous connections. Resilience. Can handle connection failures gracefully by trying another available connection. Most Node.js database drivers, e.g., PG for PostgreSQL, Mongoose for MongoDB, automatically provide connection pooling capabilities, but you need to configure them appropriately for your expected load. Practical considerations for Node.js and databases. Asynchronous drivers. Node.js database drivers are inherently asynchronous, aligning perfectly with Node.js's non-blocking I/O model. Queries return promises, allowing your application to continue processing other requests while waiting for database responses. Query optimization. Even with perfect database scaling, inefficient queries can tank performance. Always profile and optimize your SQL by adding indices, restructuring queries, or NoSQL queries. Denormalization for NoSQL. In NoSQL databases, it's common to denormalize data, duplicate data in multiple places, to optimize read performance and avoid complex joins that aren't natively supported. This, however, requires careful handling at the application level to ensure data consistency when updates occur. Caching. This is a separate, but intimately related, strategy for scaling reads from the database. A well-implemented cache can dramatically reduce database load. We will cover caching in detail in the next chapter. Transaction management. For SQL databases, be mindful of long-running transactions, which can lock tables and impact concurrency. For distributed systems, implementing complex transactions across multiple database instances or microservices is a significant challenge. Conclusion. Scaling your data layer is a multifaceted challenge, and there's no single magic bullet. It typically involves a combination of smart database choices, replication for read scaling, and, for extreme scalability, sharding. By carefully considering your data's characteristics and access patterns, and by leveraging technologies like connection pooling, and, where appropriate, NoSQL solutions, you can prevent your database from becoming the Achilles heel of your otherwise highly scalable Node.js backend. In Chapter 7, we'll see how caching can provide another powerful layer of defense against database overload, boosting performance even further. 7 caching strategies: boosting performance and reducing database load. In the previous chapter, we explored various ways to scale our databases, acknowledging that the data layer is often the performance bottleneck. While sharding and replication can help databases handle more load, there's an even more powerful technique for reducing database pressure and accelerating response times: caching. Caching is the process of storing copies of frequently accessed data in a faster, more readily available location than its original source. Think of it as keeping your most used tools on your workbench rather than constantly retrieving them from a distant shed. By serving data from a cache, you avoid the slower process of fetching it from a database, performing complex computations, or making external API calls. This significantly improves performance, reduces latency, and lowers the load on your backend services and databases, allowing them to serve more unique requests. Why cache? The triple benefit. Caching offers a compelling trio of advantages for scalable Node.js backends. Performance boost. Data retrieval from memory or a local cache is orders of magnitude faster than a database query. This directly translates to lower latency for users and a snappier application experience. Reduced database service load. Each request served from the cache is one less query hitting your database or an external API. This frees up your database to handle more complex queries or write operations, postponing the need for expensive database scaling. Cost savings. Lower database load can mean you need fewer or smaller database instances, leading to reduced infrastructure costs, especially with cloud-managed services. Where to cache? Different levels of caching. Caching can occur at various levels within your application stack. Browser cache CDN, Content Delivery Network, caches static assets, images, CSS, JavaScript, and sometimes dynamic content at the edge, closer to the user. This is the first line of defense, reducing load on your origin servers. If you serve static content from your Node.js backend, consider using a CDN. Application level, in-memory, cache. Data is stored directly within the memory of your Node.js application instance. Pros: fastest access as it avoids network calls. Cons: not shareable across multiple Node.js instances. If using horizontal scaling, data is lost if the application restarts, and memory consumption can be an issue. Suitable for data that is unique to a single process or small, frequently accessed lookup tables. Distributed cache. a dedicated external caching system accessible by all your Node.js application instances. This is the most common and powerful approach for scalable backends. Pros: shareable across all instances, high availability, often persistent across application restarts. Cons: introduces network latency, though much lower than database latency, adds another component to manage. Examples: Redis and Memcached are the de facto standards for distributed caching. Redis versus Memcached. The distributed cache powerhouses. Both Redis and Memcached are high-performance, in-memory key-value stores commonly used for caching. Memcached, simpler, designed primarily as a cache. Purely in-memory, all data resides in RAM. If the server goes down, data is lost. Good for simple key-value pairs, ideal for caching raw database query results or page fragments. Redis, more feature-rich. Besides simple key-value pairs, Redis supports various data structures like lists, sets, hashes, and sorted sets. Persistence options can persist data to disk, allowing it to recover from restarts, though this can impact performance. PubSub supports publish-subscribe messaging, useful for real-time applications or cache invalidation. Transactions and Lua scripting offers more advanced features. Suitable for caching complex objects, session management, as discussed in Chapter 4, rate limiting, leaderboards, and even acting as a simple message broker. For scalable Node.js backends, Redis is often the preferred choice due to its versatility, rich feature set, and ability to serve more use cases beyond simple caching. Common caching strategies with Node.js. Once you have a distributed cache like Redis, you need a strategy for how your Node.js application interacts with it. Cache aside, lazy loading / read-through. How it works. Application requests data, e.g., user profile. Application checks if data exists in the cache. If hit, data found in cache, return data from cache. If missed, data not found, fetch data from the database. Store a copy of the newly fetched data in the cache. Return data to the application. Pros: simple to implement. Only caches data that is actually requested, preventing caching of unused data. Cons: first request for any data will always be a cache miss and hit the database, initial latency. Data in the cache can become stale if the database changes. Node.js example, conceptual. Conceptual code for Chapter 7. Async function get user profile, user ID. Const cached profile equals await Redis client get, user, $user ID. If cached profile. Return JSON parse, cached profile. Const db profile equals await db fetch user, user ID. Go to database. If db profile. Await Redis client set, user, $user ID, JSON stringify db profile. X, 3600. Cache for 1 hour. Return db profile. Write through how it works. Application writes data. Application writes data to the cache. The cache then synchronously writes the data to the database. Pros: data in cache is always consistent with the database at the time of write. Cons: slower write operations because you're writing to 2 places. If the database write fails, the cache also needs to be updated. Not as common for web backends as cache aside. Write back, write behind, how it works. Application writes data to the cache. The cache asynchronously writes the data to the database, often in batches. Pros: very fast write operations, as the application doesn't wait for the database. Cons: data can be lost if the cache fails before persisting to the database. Data in the database might be temporarily stale. More complex to ensure durability. Cache invalidation, the hardest problem in computer science. Sir Tony Hoare famously quipped that there are only 2 hard things in computer science: cache invalidation and naming things. And he was right. Data in a cache is a copy. If the original data changes in the database, the cached copy becomes stale. Serving stale data can lead to incorrect behavior or a poor user experience. Common cache invalidation strategies. Time to live, TTL, the simplest and most common method. Data is cached for a specific duration, e.g., 5 minutes, 1 hour. After this time, it expires and is removed from the cache. The next request will result in a cache miss, forcing a fresh fetch from the database. Pros: simple to implement. Cons: data can be stale for the duration of the TTL. not ideal for highly sensitive data where immediate consistency is required. Write through /write Bengali, ben pa enus Bengali, ben akat enus Bengali ben cha enus Bengali ben dante na enus Bengali, ben akat enus invalidatation. Whenever data is written to the database or updated, explicitly remove invalidate the corresponding entry from the cache. Pros, ensures fresh data after an update. Cons, requires careful implementation for every write path. Can be complex in distributed microservices where multiple services might update the same underlying data. Background refresh. Periodically refresh cache data, even if it hasn't expired, especially for critical data that needs to be as fresh as possible. This can be combined with TTL. For a scalable Node.js backend, you'll often use a combination of TTL for passive expiration and explicit invalidation for active updates. Practical considerations for Node.js caching. Granularity, cache at the right level. Don't cache everything. Cache results of expensive queries, frequently accessed objects, users, products, or rendered page fragments. Key design. Create clear, consistent cache keys, e.g. user, 123, product, category, shoes. Serialization. When storing complex objects in Redis, you'll need to serialize them, e.g., using JSON stringify and JSON parse in Node.js as Redis stores string data. Error handling. Implement robust error handling for cache interactions. If the cache is unavailable, your application should gracefully fall back to the database, fail-safe. Monitoring. Monitor your cache hit rates, miss rates, and eviction rates. This tells you how effective your caching strategy is. A high hit rate indicates a good cache. Security. Ensure sensitive data is handled appropriately in the cache, e.g., avoiding caching raw passwords. Cache warming. For critical data, you might pre-populate the cache before peak traffic or after deployment to ensure immediate cache hits. The power of layered caching. The most robust and performant systems often employ multiple layers of caching. A user might access content from browser cache, stored on their local device. CDN, closer to their geographic location. Load balancer reverse proxy cache, Nginx or a similar service can cache full responses. Distributed Node.js cache, Redis, for dynamically generated content specific to your application. Database read replica. If the cache misses, the read goes to a replica, not the primary database. This layered approach ensures that the vast majority of requests are served extremely quickly from a cache, reserving your database resources for more complex, dynamic, or write-heavy operations. By intelligently implementing caching strategies, particularly with distributed solutions like Redis, your Node.js backend can handle a significantly higher volume of read traffic and improve overall system performance without constantly needing to scale up your primary data stores. This frees up your database to focus on its core strength, durable and consistent data storage. With our backend now fast and efficient, our next concern must be securing it, which is the focus of Chapter 8. 8. Securing scale. Authentication, authorization, and data protection. As your Node.js backend scales to handle more users and more data, security stops being an afterthought and becomes a paramount concern. A security breach, whether it's a data leak, unauthorized access, or a denial of service attack, can cripple an application, erode user trust, and incur significant financial and reputational damage. When operating at scale, the attack surface expands and vulnerabilities can have a broader impact. This chapter will guide you through crucial security considerations for scalable Node.js backends, focusing on authentication, verifying who a user is, authorization, determining what a user can do, and general data protection principles. The challenge of statelessness in distributed systems. In Chapter 4, we discussed how horizontal scaling favors stateless Node.js processes, externalizing session data to a shared store like Redis. This is excellent for scalability, but it changes how we handle user identity compared to traditional, stateful session-based systems. Stateful sessions versus stateless tokens. Stateful sessions. In a traditional approach, after a user logs in, a unique session ID is generated and stored on the server, e.g., in memory or a database. This ID is then sent to the client, usually in a cookie. For every subsequent request, the server looks up the session ID to confirm the user's identity and permissions. Pros: simpler to implement initially, easy to revoke sessions immediately. Cons: not inherently scalable for distributed systems. If the session is stored on a specific server, requests must be sticky to that server, reducing load balancing efficiency, or sessions must be externalized, adding complexity. Stateless tokens, e.g., JWTs. With stateless tokens, once a user logs in, the server generates a cryptographically signed token, like a JSON web token, JWT, containing information about the user and their permissions. This token is then sent back to the client, e.g., in an authorization header. The server doesn't store any session state itself. For subsequent requests, the server verifies the token's signature, extracts user information from it, and directly uses that information for authorization. Pros: highly scalable. No session data needs to be shared or synchronized across server instances. Any Node.js instance can validate the token independently. Decoupled. The authentication service can be separate from the resource serving services. Mobile-friendly, tokens can be easily passed in headers, suitable for mobile apps. Cons: lack of immediate revocation. Once a token is issued, it's typically valid until it expires. Revoking a token early, e.g., if a user logs out or changes a password, requires additional mechanisms, e.g., a blacklist revocation list in RIDIs. Token size. Storing too much data in the token can increase request size. For scalable Node.js backends, stateless tokens, particularly JWTs, are the preferred method for authentication due to their inherent scalability advantages. Authentication, verifying who you are. Authentication is the process of confirming a user's identity. Implementing JWTs with Node.js, login endpoint, when a user provides credentials, username, password. The Node.js server authenticates them, e.g., hashes the password and compares it to the stored hash. If successful, it creates a JWT using a secret key. The JWT typically contains a header, a payload, e.g., user ID, roles, expiration time, and a signature. The signed JWT is sent back to the client. Protected endpoints. For subsequent requests to protected routes. The client includes the JWT in the authorization, bearer token header. The Node.js server, using a middleware library like JSON Web Token, verifies the token's signature, using the same secret key, and checks its expiration. If valid, the user's information from the token payload is available to the request handler. Security considerations for JWTs. Secret key management. The secret key used to sign JWTs must be kept absolutely secret and should be stored securely, e.g., in environment variables, a secrets management service, not hard-coded. Expiration time, exp claim. Always set a short expiration time for access tokens, e.g., 15 minutes to 1 hour. This limits the window of opportunity for stolen tokens. Refresh tokens. For a better user experience and robust security, use a combination of short-lived access tokens and longer-lived refresh tokens. The client sends refresh tokens to a dedicated endpoint to obtain a new access token without re-authenticating repeatedly. Refresh tokens should be stored securely, e.g., in an HTTP-only cookie, and can be easily revoked in a database or RIDIs if compromised. Token storage on client. Advise clients to store access tokens securely, e.g., in memory for single-page applications, though local storage or HTTP-only cookies are also common depending on the risk model. Authorization. What you can do. Authorization is the process of determining what actions an authenticated user is permitted to perform. Common authorization models. Role-based access control, RBAC. Users are assigned to roles, e.g., admin, editor, guest. Permissions are then assigned to roles. Implementation. The user's role can be included in the JWT payload. Your Node.js root handlers or middleware then check if the authenticated user's role has the necessary permission to access a resource or perform an action. Conceptual middleware example. Function authorize roles required roles. Return rec raise next equals. Const user roles equals rec.user roles. Assuming user roles are on rec.user, from JWT verification. Const has permission equals user roles. Sum role equals required roles dot includes role. If has permission. Next, else. Res status 403. Send forbidden, insufficient permissions. Usage and route. app.delete/API/product/d authorize roles admin, product manager, delete product. Attribute-based access control, ABAC, more granular than RBAC. Access decisions are based on attributes of the user, e.g., department, location, the resource, e.g., document type, confidential, and the action, e.g., read, write. Implementation, more complex, often requires a dedicated authorization engine or policy enforcement points. Scalable ABAC systems often use rules engines. Ownership-based authorization. A user can only access modify resources they own. Implementation. Check if rec.userid matches the resource ownerid retrieved from the database. Best practices for authorization. Default deny. By default, deny all access and explicitly grant permissions. Least privilege. Grant users only the minimum permissions necessary to perform their tasks. Centralize authorization logic. Avoid scattering authorization checks throughout your codebase. Use middleware or dedicated authorization modules. Combine models. It's common to use RBAC for broad categorizations and then fine-tune with ownership checks or simple ABAC rules. Rate limiting, preventing abuse and overload. As your Node.js backend scales, it becomes a target for various forms of abuse, from brute force login attempts to malicious denial of service (DoS) attacks. Rate limiting is a defense mechanism that restricts the number of requests a user, IP address, or API key can make to an API within a given timeframe. Benefits of rate limiting for scalability. Mitigate DoS attacks, prevents a single entity from overwhelming your servers. Prevent brute force attacks, limits the number of login attempts, making it harder to guess passwords. Fair usage. Ensures fair access to your API for all users. Cost control. Prevents excessive usage that could incur unexpected costs for external services. Implementation with Node.js. Rate limiting often involves distributed counters, commonly implemented using RIDIs as discussed in Chapter 7. Store IP address, last seen timestamp, request count in RIDIs. For each incoming request, check the counter for the IP user. If within the limit, increment the counter and process the request. If over the limit, return a 429 too many requests status code. Adjust the counters based on the time window. Several Node.js libraries provide easy-to-use rate-limiting middleware, e.g., express rate limit. Data protection, encryption and integrity. Protecting your data, both in transit and at rest, is non-negotiable for any scalable application. Data in transit, HTTPS SSL TLS. Mandatory. Always use HTTPS, HTTP Secure, for all communication between clients and your Node.js backend. This encrypts data, preventing eavesdropping and tampering. Implementation, typically handled at the load balancer or web server, e.g., Nginx level, which terminates SSL and forwards unencrypted traffic to your Node.js application, or you can implement it directly in Node.js, though that's less common for production. Your cloud provider will have simple ways to enable this. Data at rest database encryption. Encrypt sensitive data. For highly sensitive data, e.g., personally identifiable information, payment details, stored in your database, consider encrypting it at the application level before storing it. Database level encryption. Many databases offer encryption at rest, which encrypts entire database files, though this doesn't protect against direct SQL injection attacks. Hashing passwords, critical. Never store raw passwords. Always hash them using a strong, one-way hashing algorithm like bcrypt with a salt. Node.js libraries like bcryptos make this easy. Input validation and sanitization. Protect against injection attacks. All user input must be rigorously validated and sanitized to prevent SQL injection, cross-site scripting XSS, and other injection attacks. Framework tools. Use validation libraries, e.g., Joy, Yup, Express Validator, in your Node.js application. Security is an ongoing process. Building a secure, scalable backend isn't a one-time task. It's a continuous process. Regular security audits periodically review your application and infrastructure for vulnerabilities. Dependency management regularly update your Node.js dependencies to patch known vulnerabilities. Tools like npm audit are invaluable. Principle of least privilege apply to users, services, and infrastructure. Security headers implement HTTP security headers, e.g., CSB, X-frame options, in your Node.js Express applications or through your reverse proxy. Logging and monitoring ensure comprehensive logging of security-related events and have alerts in place for suspicious activity. We'll cover this in Chapter 11. By adopting these robust security practices, especially those adapted for the stateless nature of scalable Node.js deployments, you can build systems that not only perform well under load, but also protect your users and your business from malicious actors. With our backend now secure, the next logical step is to consider how we design the APIs that clients will interact with, ensuring they are also resilient and scalable. 9. API design for resilience and scalability. REST, GraphQL, and beyond. Up to this point, we focused internally on how to build and scale the various components of your Node.js backend, from leveraging its unique architecture to managing databases and ensuring security. Now, it's time to consider the external face of your backend, the Application Programming Interface, API. The way you design your API directly influences not only how easy it is for client applications, web, mobile, third-party services to consume your backend, but also its overall scalability, performance, and resilience. A well-designed API can simplify client development, reduce network traffic, and make your backend more adaptable to future change. Conversely, a poorly designed API can lead to inefficient data fetching, contribute to backend load, and hinder application growth. This chapter will delve into the principles of designing scalable APIs and explore different architectural styles, including the widely adopted REST, the increasingly popular GraphQL, and the high-performance gRPC. Fundamental principles of scalable API design. Regardless of the architectural style you choose, certain principles are universal for designing APIs that scale. Statelessness, if applicable. For REST-TFL APIs, clients should contain all the information needed to process the request. The server should not store any client context between requests. This aligns perfectly with the horizontal scaling strategies we discussed in Chapter 4, where any Node.js instance might serve a request. Clear, consistent naming and structure. Use intuitive paths, resource names, and request-response formats. Consistency reduces the learning curve for developers and minimizes errors. Versioning. As your API evolves, you'll inevitably need to make changes that break backward compatibility. Versioning V1 users, V2 users, allows clients to migrate gracefully without breaking existing integrations. Error handling, predictable responses. Provide clear, consistent, and informative error messages, e.g., using HTTP status codes for REST or specific error types for GraphQL. This helps client developers debug issues rapidly. Filtering, sorting, and pagination. Do not return all data when only a subset is needed. Allow clients to request specific data using query parameters, e.g., /products, category equals electronics and limit equals 10, and offset equals 20. This reduces payload size and database load. Security, authentication, and authorization. As discussed in Chapter 8, secure your API endpoints with appropriate authentication and authorization mechanisms. Idempotency for mutations. An idempotent operation produces the same result no matter how many times it is executed. For operations like creating or updating resources, provide a way for the client to ensure that retrying a request due to network error, for instance, doesn't result in duplicate data being created. This can be achieved with unique request IDs. HATOAS for REST, hypermedia as the engine of application state. For REST-TFL APIs, this means including links to related resources or available actions within the API response, allowing clients to navigate the API dynamically without hard-coding URLs. While often debated for its practical adoption, It's a core principle of truly REST-TFL APIs. REST-TFL APIs, representational state transfer. REST is an architectural style, not a protocol, that leverages standard HTTP methods, GET, POST, PUT, delete, and a resource-oriented approach. It's the most common API design style for web services. Key concepts: resources. Everything is a resource, e.g., users, products 123. HTTP methods: GET, retrieve a resource, safe, idempotent. POST, create a new resource or submit data, not idempotent. PUT, update an existing resource, idempotent, replaces the entire resource. Patch, partially update an existing resource, not necessarily idempotent. Delete, remove a resource, idempotent. Statelessness, each request contains all information needed. JSON or XML, primary data interchange format. Scalability considerations for REST. Caching. REST's use of HTTP methods allows for powerful caching at various levels: browser, CDN, reverse proxy, application cache for GET requests, significantly reducing backend load. Statelessness directly supports horizontal scaling of Node.js instances. Simplicity. Being built on HTTP, REST APIs are relatively easy to understand and consume, speeding up client development. Challenges with REST at scale. Underfetching and overfetching. Underfetching. A single client view might require multiple API calls to gather all necessary data, e.g., fetching a user, then making another call to get their orders. This increases network round trips and latency. Overfetching. An API might return more data than a client actually needs, wasting bandwidth and processing time. Versioning complexity. Managing multiple API versions can become cumbersome. Node.js frameworks like Express.js and Fastify are excellent for building REST-TFL APIs, providing routing, middleware, and request response handling. GraphQL, client-driven data fetching. GraphQL is a query language for your API and a runtime for fulfilling those queries with your existing data. It emerged from Facebook's need to efficiently fetch data for its mobile applications. Key concepts: single endpoint. You expose a single HTTP endpoint, usually post/GraphQL, to interact with your entire API. Schema definition language, SDL. You define a strong type system for your data. This schema acts as a contract between client and server. Client-driven queries. Clients send a query string specifying exactly what data they need, and the server responds with precisely that data and nothing more. This eliminates underfetching and overfetching. Resolvers. On the server, resolvers are functions that fetch the data for each field in a GraphQL query. Scalability considerations for GraphQL. Eliminates N+1 problem, often. By allowing clients to specify relationships directly in one query, GraphQL can reduce the number of round trips to the server and database, improving performance. Reduced bandwidth. Clients retrieve only the data they need, saving bandwidth, which is crucial for mobile clients or slow networks. Simplified client development. Clients declare their data requirements, leading to more robust client code and less glue code. Real-time capabilities, subscriptions. GraphQL has built-in support for real-time data updates via subscriptions, often implemented over WebSockets, pushing data to clients as it changes. Challenges with GraphQL at scale. Caching complexity. Standard HTTP caching mechanisms, like CDNS, are less effective with a single post endpoint and dynamic queries. Caching often needs to be implemented at the application level, e.g., using Redis for resolver caching. Performance optimization. Complex, deep queries from clients can be expensive for your backend. Requires careful implementation of data loaders and query cost analysis. Learning curve. Steeper learning curve for both server and client developers compared to REST. File uploads. Not natively handled as cleanly as in REST, requires specific workarounds. Node.js has excellent libraries for building GraphQL APIs, such as Apollo Server and GraphQL.js. gRPC. High-performance, microservices communication. While REST and GraphQL are excellent for client-server communication, gRPC, Google Remote Procedure Call, is a modern, open-source high-performance RPC, remote procedure call. Framework primarily designed for efficient communication between services, microservices. Key concepts: protocol buffers, protobuf, uses protocol buffers for defining service interfaces and message structures. Protobuf is a language-agnostic, platform-agnostic, extensible mechanism for serializing structured data. It's much more efficient, smaller messages, faster serialization/deserialization than JSON or XML. HTTP, built on HTTP2, which enables features like multiplexing, multiple requests over a single connection, streaming, bidirectional streaming, and header compression. Code generation. Using protobuf definitions, gRPC generates client and server-side code in various programming languages, including Node.js, simplifying development and ensuring consistency. Scalability considerations for gRPC. Extreme performance. Due to protobuf and HTTP2, gRPC offers significantly faster communication and lower latency than REST over HTTP 1.1 with JSON payloads. Efficient resource usage. Smaller message sizes and persistent connections reduce network and CPU overhead. Strong typing. Protobuf enforces strong typing, reducing runtime errors and improving maintainability in polyglot microservice environments. Streaming supports 4 types of service methods, including client-side streaming, server-side streaming, and bidirectional streaming, which are powerful for real-time data flows without WebSockets overhead. Challenges with gRPC at scale. Human readability. Protobuf messages are binary, making them less human-readable than JSON for debugging. Browser support. Browsers don't natively support HTTP2 frames, so gRPC clients in browsers require a proxy like gRPC Web. Not for public APIs. Typically not exposed directly to external clients, more suited for internal service-to-service communication. Learning curve. Protobuf definitions and the RPC paradigm can have a steeper learning curve than REST for new developers. Node.js has official gRPC packages, making it a viable choice for high-performance internal microservices communication in a scalable architecture. Choosing the right API style for your Node.js backend. REST, best for most public-facing APIs, simple CRUD, create, read, update, delete operations, resources that map well to HTTP verbs, applications that benefit heavily from traditional HTTP caching. Scalability. Excellent, heavily reliant on HTTP caching and statelessness. GraphQL, best for clients that need highly flexible data fetching, e.g., mobile apps, complex UIs, applications with many different client types having varied data requirements, microservice aggregations, via a GraphQL API gateway. Scalability, achieved by minimizing network round trips and data transfer, but requires careful server-side resolver optimization and internal caching. gRPC, best for high-performance internal microservice communication, streaming data, polyglot environments where different services are written in different languages. Scalability, built for efficiency and raw speed, ideal for the demanding communication needs between distributed components. Many scalable architectures leverage a combination of these: a public REST or GraphQL API for external clients, and gRPC for internal service-to-service communication, all tied together by well-designed principles. The ultimate goal is to enable efficient communication that supports your application's growth without compromising performance or maintainability. With our backend architected for scale and secured, the next logical step is to consider how we deploy and manage these systems in a production environment. 10. Deployment and DevOps, orchestrating your scalable Node.js applications. You've designed a scalable Node.js backend, fortified it with caching, and crafted robust APIs. But an application, however perfectly engineered, serves no purpose until it's running reliably in a production environment, accessible to users. This is the domain of deployment and DevOps, the practices and tools that bridge the gap between development and operations, ensuring your application can be built, tested, deployed, and managed efficiently and reliably at scale. For scalable backends, especially those adopting microservices or distributed patterns, manual deployment becomes a nightmare. automation, consistency, and a clear understanding of your infrastructure are paramount. The rise of containerization, Docker. The first cornerstone of modern scalable deployments is containerization, and the dominant technology here is Docker. Imagine you've built a Node.js application that relies on specific Node.js versions, NPM packages, environment variables, and possibly even system-level dependencies, like image processing libraries. If you move this application to another server, there's no guarantee it will run exactly as it did on your development machine. This problem, "it works on my machine," is what containers solve. A Docker container packages your application, along with all its dependencies, libraries, and configurations, into a single, isolated, and portable unit. It's like a lightweight, self-contained virtual machine that runs your application consistently across different environments: development, testing, staging, production. Benefits of Docker for scalable Node.js applications: consistency, build once, run anywhere. Eliminates environment-related bugs. Isolation. Each container runs in isolation, preventing conflicts between applications or dependencies. Portability. A Docker image, the blueprint for a container, can be run on any system with Docker installed, from a developer's laptop to a cloud server. Efficiency. Containers share the host OS kernel, making them much lighter and faster to start than traditional virtual machines. Scalability. Containers are easily replicated. Need more instances of your Node.js microservice? Just spin up more containers. How Node.js goes into a Docker container. You create a Docker file, a text file that contains instructions for building your image, e.g., specifying a base Node.js image, copying your application code, installing NPM dependencies, exposing ports. You build the image using Docker build. You run the image as a container using Docker run. This process streamlines the operational aspects of deploying Node.js applications, making them repeatable and robust. Orchestrating containers, Kubernetes. Once you have a dozen, 100, or even thousands of Docker containers that need to run, be managed, scaled, and updated, manually handling them becomes impossible. This is where container orchestration platforms come in, with Kubernetes, often shortened to K8s, as the undisputed leader. Kubernetes is an open-source system for automating deployment, scaling, and management of containerized applications. It provides a platform for running and managing your containers across a cluster of machines. Key Kubernetes concepts relevant to scalable Node.js. Pods, the smallest deployable units in Kubernetes. A pod typically encapsulates one or more containers that are tightly coupled and share resources. Your Node.js application will run inside a container within a pod. Deployments. An object that declares the desired state for your application, e.g., always run 5 replicas of my Node.js service. Kubernetes automatically manages creating, updating, and scaling pods to match this desired state. Services, an abstract way to expose an application running on a set of pods as a network service. This provides a stable IP address and DNS name, allowing your front-end or other microservices to discover and communicate with your Node.js backend without knowing the specific pod IPs, which can change. Ingress manages external access to the services in a cluster, typically HTTP, HTTPS routes. It acts as the entry point for your client applications to reach your Node.js backend services. Replica sets ensures that a specified number of pod replicas are running at any given time. Horizontal pod autoscaler, HPA, automatically scales the number of pod replicas for your Node.js application based on observed CPU utilization or other custom metrics. This is a crucial feature for elastic scalability. Nodes, the actual machines, physical or virtual, that run your pods. Cluster, a set of nodes collectively managed by Kubernetes. Benefits of Kubernetes for Node.js scalability. Automated scaling. Automatically adds or removes Node.js pods based on demand, ensuring your application always has enough capacity. Self-healing. If a Node.js pod crashes or a node fails, Kubernetes automatically restarts the pod or reschedules it to a healthy node. Automated rollouts and rollbacks. Deploy new versions of your Node.js application with zero downtime. If a new version has issues, Kubernetes can automatically roll back to the previous stable version. Service discovery and load balancing. Built-in mechanisms for services to find each other and distribute traffic efficiently. Resource management. Efficiently allocate CPU and memory to your Node.js containers. While Kubernetes has a steep learning curve, its power in automating and managing complex distributed systems, including Node.js microservices, makes it an indispensable tool for achieving high scalability and operational efficiency. Many cloud providers offer managed Kubernetes services, e.g., AWS EKS, Google Kubernetes Engine GKE, Azure AKS, to simplify its adoption. Continuous integration, continuous deployment, CI/CD. For fast-moving, scalable applications, manual deployment processes are a bottleneck. CI/CD pipelines automate the steps involved in delivering software, from code commit to production deployment. Continuous integration, CI, developers frequently integrate their code into a shared repository. Each integration is verified by an automated build and automated tests. This helps detect integration issues early. Process. Developer commits code CI server e.g., Jenkins, GitLab CI, GitHub Actions, detects change, pulls code, installs Node.js dependencies, runs linting static analysis, runs unit and integration tests. Continuous delivery, CD, ensures that code is always in a deployable state after the CI process. You can manually trigger deployments to production. Continuous deployment, CD, takes continuous delivery a step further by automatically deploying every change that passes all automated tests into production. Benefits of CI/CD for Node.js scalability. Faster release cycles. Deliver new features and bug fixes to users more quickly. Improved quality. Automated tests catch bugs early before they reach production. Reduced risk. Smaller, more frequent deployments are less risky than large, infrequent ones. Increased reliability. Consistent, automated processes reduce human error in deployments. Faster recovery. If a problem arises, a fast rollback to a previous version is possible. For Node.js applications, a typical CI/CD pipeline would involve building Docker images, pushing them to a container registry, and then updating Kubernetes deployments to roll out the new version. Deployment strategies for zero downtime. When updating a scalable Node.js backend in production, minimizing downtime is crucial. Several strategies achieve this: rolling updates, built into Kubernetes deployments. How it works. Gradually replaces old pods with new ones, one by one or in small batches. The load balancer continues to send traffic to the old pods until new ones are healthy. Pros: simple, built into Kubernetes, zero downtime. Cons: if the new version has a bug, it will gradually affect all users. Difficult to roll back quickly. Blue-green deployment. How it works. You run two identical production environments, blue, the current live version, and green, the new version. Traffic is initially directed to blue. Once green is fully deployed and tested, you switch the load balancer to direct all traffic to green. Blue is kept as a fallback. Pros: zero downtime. Instant rollback by switching traffic back to blue. Cons: requires double the infrastructure, which can be costly. Canary deployment. How it works. A small subset of user traffic is routed to the new version, the canary. If the canary performs well, more traffic is gradually shifted until the new version is fully rolled out. Pros: minimizes risk by testing new versions on a small user base. Allows for early detection of issues. Cons: more complex to set up and monitor. Requires sophisticated traffic routing and monitoring tools. Infrastructure as code, ISC. Finally, for consistency and scalability, managing your infrastructure manually is not sustainable. Infrastructure as code, ISC, involves managing and provisioning computing infrastructure, like servers, networks, load balancers, and monitoring, using machine-readable definition files, rather than through physical hardware configuration or interactive configuration tools. Tools like HashiCorp Terraform or CloudFormation, AWS, allow you to define your entire infrastructure, including Kubernetes clusters, databases, and network configurations, in code. This means your infrastructure is version-controlled, repeatable, and deployable with automated pipelines, just like your Node.js application code. By embracing Docker, Kubernetes, CI/CD, and infrastructure as code, your Node.js backend can be deployed, scaled, and managed with confidence, ensuring high availability and rapid iteration capabilities, even as your application grows to serve millions of users. These DevOps practices are the operational backbone of any truly scalable system. Next, we turn our attention to the critical task of understanding how our deployed systems are performing, monitoring, logging, and alerting. 11. Monitoring, logging, and alerting. Keeping your backend healthy and responsive. You've painstakingly designed, built, and deployed a scalable Node.js backend. But once it's out in the wild, exposed to real users and real traffic, how do you know if it's actually healthy? Is it performing as expected? Are there any hidden bottlenecks? Are users experiencing errors? The answer lies in observability through robust monitoring, logging, and alerting strategies. Ignoring observability is akin to driving a car with a blindfold on. You might get somewhere, but you're bound to crash eventually. An observable system provides deep insights into its internal state, allowing you to understand its behavior, diagnose problems quickly, and ensure sustained performance and reliability. The 3 pillars of observability. Observability rests on 3 foundational pillars: logs, detailed, time-stamped records of discrete events that happen within your Node.js application or infrastructure. They tell you what happened. Metrics, quantifiable measurements that are aggregated over time, providing insights into the overall health and performance of your system. They tell you how much or how often something is happening. Traces represent the end-to-end journey of a single request or transaction through a distributed system, showing how different services interact. They tell you why something happened by showing causality across services. 1. Logging, the narrative of your application. Logs are the narrative of your application, capturing events like request arrival and departure, function calls and their arguments, database queries, errors and warnings, user actions, e.g. login purchase. Best practices for Node.js logging. Structured logging. Instead of plain text messages, log data in a structured format, typically JSON. This makes logs easily machine-readable, parsable, and searchable by logging tools. Example of structured logging. Console log, JSON stringify. Timestamp new date to ISO string. Level, info. Service, user service. Action, user login. Userid, user123. IP address, 192.168.1.1. Message, user logged in successfully. Example of error logging. Try, some operation that fails. Catch error, console error, JSON stringify. Timestamp new date to ISO string. Level, error. Service, product service. Action, create product. Producted, new product fills eyes. Error, error message. Stack, error stack. Message, failed to create product. Log levels. Use appropriate log levels, e.g. debug, info, warn, error, fatal, to filter log output based on severity. Contextual information. Include relevant context with each log message, e.g. requested, userid, transactioned. This is critical for correlating events across different parts of your application and indeed, across different microservices. Avoid sensitive data. Never log sensitive information like passwords, API keys, or personal financial details. Centralized logging. Collect logs from all your Node.js instances and other services into a central logging system. This enables searching, filtering, analysis, and dashboarding across your entire infrastructure. Popular choices include Elk Stack, Elasticsearch for storage and search, Logstash for parsing, Kibana for visualization. Low-key Grafana Labs, designed for logs, pairs well with Prometheus metrics. Managed cloud services, AWS CloudWatch logs, Google Cloud Logging, Azure Monitor logs. Node.js logging libraries like Winston or Pinot facilitate structured logging and integration with various transport layers. 2. Monitoring, the pulse of your system. Monitoring involves collecting numerical data, metrics, about your system's performance and health over time. Metrics answer questions like, How many API requests are we handling per second? What's the average response time for our user's endpoint? What's the CPU utilization of our Node.js pods? How much memory are our Node.js processes consuming? What's the error rate for our authentication service? Key performance indicators, KPIs for Node.js backends, request rate, total number of requests per second, error rate, percentage of requests returning errors, e.g., HTTP 5XX codes, response latency, average P95, 95th percentile, and P99, 99th percentile response times for various endpoints. High percentiles are crucial for identifying long-tail latency issues affecting a small but important percentage of users. Resource utilization, CPU, memory, disk I/O, network I/O usage for your Node.js processes and underlying infrastructure. Event loop latency, a Node.js-specific metric that indicates how often the event loop is blocked. High latency suggests CPU-bound tasks or long-running synchronous code. Garbage collection activity, frequency and duration of garbage collection cycles, which can impact performance. Tools for monitoring, Prometheus, a powerful, open-source monitoring system that collects metrics via a pull model. Your Node.js app exposes a metrics endpoint, very popular in Kubernetes environments. Grafana, an open-source analytics and visualization platform that allows you to create beautiful, customizable dashboards from various data sources, including Prometheus, Elasticsearch, and cloud monitoring services. Managed cloud services, AWS CloudWatch, Google Cloud Monitoring, Stackdriver, Azure Monitor. Application performance monitoring, APM tools, commercial solutions like New Relic, Datadog, Dynatrace, or open-source alternatives like OpenTelemetry. These offer more comprehensive insights, including distributed tracing and code-level profiling. Your Node.js application can easily expose metrics using libraries that integrate with Prometheus, e.g., Prom Client, or send data to APM agents. 3. Alerting, waking you up when it matters. Monitoring is for understanding. Alerting is for action. It's about automatically notifying the right people or systems when predefined thresholds are crossed or abnormal behavior is detected. You don't want to constantly watch dashboards. You want to be told when something needs attention. Key principles for alerting, actionable alerts. Alerts should clearly indicate what the problem is, where it is, and why it's happening. Avoid noise alerts that lead to alert fatigue. Contextual information. Include enough context in the alert notification to help the recipient quickly understand the severity and scope of the problem. Targeted delivery. Send alerts to the appropriate channels, e.g., Slack, PagerDuty, Opsgenie, email, and to the right on-call team members. Levels of severity. Distinguish between critical page on-call, warning send to a less intrusive channel, and informational log-only alerts. Symptom-based alerts. Focus on alerting on symptoms, what the user experiences, e.g., high error rate, slow response times, rather than just causes, e.g., high CPU. While root cause alerts can be valuable, symptom-based alerts ensure you're addressing immediate user impact. Example alerting scenarios for Node.js. High error rate. If the HTTP 5XX error rate from your Node.js API endpoint exceeds 1% for 5 minutes. Slow response times. If P99 latency for critical API requests exceeds 500 ms for 10 minutes. Disk full if a log volume on a server is nearing capacity. Service unavailability if a minimum number of Node.js pod replicas are not running. Event loop blockage if event loop latency consistently stays above a certain threshold. Alerting systems, like Prometheus Alert Manager or integrated in cloud monitoring services, allow you to define rules and notification channels. Distributed tracing, following the request's footsteps. In a microservices architecture, a single user request might traverse multiple Node.js services, database calls, message queues, and external APIs. If an error occurs or performance degrades, identifying the exact component responsible can be a needle in a haystack. Distributed tracing allows you to visualize the flow of a single request across all the services it interacts with. Each operation within a trace is called a span, with associated metadata like timing, errors, and relevant tags. Benefits of distributed tracing: root cause analysis. Pinpoint the exact service or component causing a delay or error. Performance optimization. Identify bottlenecks in interservice communication. Understanding service dependencies. Visualize how your different Node.js microservices depend on each other. Tools for distributed tracing. OpenTelemetry, an open-source project that provides APIs, SDKs, and tools to instrument, generate, collect, and export telemetry data, metrics, logs, and traces. It's becoming the industry standard. Jaeger, Zipkin, open-source distributed tracing systems. Commercial APM tools often include robust tracing capabilities. Instrumenting your Node.js application and other services in your stack with OpenTelemetry can provide invaluable insights into the behavior of your distributed system at scale. Conclusion: monitoring, logging, and alerting are not optional extras. They are fundamental for building and maintaining robust, scalable Node.js backends. They provide the visibility necessary to understand how your system behaves under load, quickly identify and resolve issues, and ultimately ensure a continuously high-quality experience for your users. A well-implemented observability strategy is what allows you to sleep soundly, knowing your scalable application is humming along, and you'll be the first to know if it isn't. In our final chapter, we'll look to the future, discuss emerging trends, and how to continuously improve your scalable backend. 12. Future proofing your backend, emerging trends and continuous improvement. Congratulations! You've journeyed from understanding the fundamentals of scalability and Node.js's unique architecture. Through architectural choices, horizontal scaling, asynchronous processing, data layer management, security, API design, and finally, deployment and observability. You now possess a comprehensive toolkit for building robust, high-performance, and scalable Node.js backends. But the world of technology never stands still. New paradigms emerge, existing tools evolve, and user expectations continuously rise. To effectively future-proof your Node.js backend and remain a leading practitioner, a commitment to continuous learning and adaptation is essential. This final chapter will touch upon some emerging trends and offer advice on sustaining excellence. Emerging trends shaping scalable backends. WebSockets for real-time applications. While traditional HTTP REST is excellent for request-response patterns, many modern applications require real-time, bidirectional communication, e.g., chat applications, collaborative tools, live dashboards, gaming. WebSockets provide persistent, low-latency connections between the client and server. Node.js, with its event-driven, non-blocking nature, is exceptionally well-suited for building WebSocket servers due to its ability to handle a massive number of concurrent connections efficiently. Libraries like Socket.io or WS make WebSocket implementation straightforward in Node.js. Scalability consideration. Managing state and distributing messages across multiple WebSocket servers, when horizontally scaled, can be complex, often requiring an external message broker, like Redis PubSub, to coordinate messages between instances. Edge computing and serverless expansion. As applications become more distributed, the concept of edge computing processing data closer to the source of data generation or consumption is gaining traction. This reduces latency and bandwidth usage. Serverless functions, FAS, which we touched upon in Chapter 3, are a natural fit for edge scenarios, allowing code to be deployed and executed in geographically distributed locations, e.g., Cloudflare Workers, AWS Lambda at Edge. Node.js's lightweight nature and fast cold starts make it an excellent choice for these distributed serverless environments. AI/ML integration. Artificial intelligence and machine learning are no longer niche. Integrating AI/ML models into backend services for tasks like recommendations, fraud detection, content moderation, or natural language processing is becoming common. Scalability consideration. While the model training is often done in specialized environments, running inference, using the trained model to make predictions, can add significant computational load to your Node.js backend. You might offload inferences to dedicated microservices, specialized inference engines, e.g., TensorFlow serving, or even serverless GPUs, interacting with them asynchronously. Node.js can act as the orchestration layer for these AI-driven workflows. Observability maturation, OpenTelemetry. As discussed in Chapter 11, observability is critical. The adoption of OpenTelemetry as the open-source standard for collecting traces, metrics, and logs is rapidly growing. This reduces vendor lock-in and simplifies the instrumentation of complex, distributed systems. Investing in OpenTelemetry for your Node.js applications will be key to maintaining deep visibility into your future-proofed systems. WebAssembly, WASM, and WASI, WebAssembly System Interface. WebAssembly is a new type of code that can be executed in modern web browsers and, increasingly, outside the browser, including on servers. WASI extends WebAssembly to access system resources securely. While nascent for general backend development, WASM allows you to run performance-critical code written in languages like Rust, C++, or Go directly in your Node.js applications or as standalone components, potentially offering speed advantages for CPU-bound tasks without resorting to separate microservices. This is an exciting space to watch. Continuous improvement, the path to lasting scalability. Building a scalable backend is not a one-and-done project. It's a continuous journey of optimization, learning, and adaptation. Embrace incremental change. Resist the urge to rewrite everything from scratch. Instead, identify bottlenecks, refactor specific components into microservices, if appropriate, and incrementally optimize as needed. The monolith first, then extract strategy is often the safest path. Monitor constantly, optimize lazily. Good monitoring, Chapter 11, tells you where to optimize. Don't optimize prematurely. Focus on parts of your system that are genuinely causing performance issues or scalability bottlenecks. Trust your metrics. Regularly review architecture and code. Hold regular architectural reviews. As your team grows and technology evolves, what was efficient yesterday might be a bottleneck tomorrow. Ensure your Node.js codebase remains clean, maintainable, and adheres to best practices. Stay up to date with Node.js and ecosystem. Node.js is a rapidly evolving platform. Keep an eye on new Node.js releases, V8 engine improvements, and emerging libraries and frameworks, e.g., Fastify for performance-critical APIs, Nest.js for highly structured applications. This doesn't mean jumping on every new fad, but understanding what new capabilities are available. Foster a culture of learning and DevOps. Encourage your team to continuously learn new technologies and best practices. Promote a strong DevOps culture where developers feel ownership of their code through to production, understanding its performance and operational characteristics. Security never sleeps. The threat landscape constantly changes. Regularly review your security posture, keep dependencies updated, conduct security audits, and stay informed about new vulnerabilities. Final thoughts. Building scalable backends, especially with Node.js, is both an art and a science. It requires a deep understanding of the underlying technology, careful architectural choices, disciplined implementation, and a commitment to operational excellence. Node.js provides a robust and efficient foundation, particularly for I/O-bound, concurrent workloads. By leveraging its strengths, understanding its constraints, and applying the principles of distributed systems design, you are well equipped to build the next generation of resilient, high-performance, and truly scalable applications. The quest for scale is continuous. May your backends remain robust, your deployments swift, and your users delighted. Begin building.